All right, so if we look at our warm up here, we've got the limit, right? As x approaches 3, from which side? Both sides. Yeah, both sides of this rational function. It's a cubic polynomial over a quadratic. So the limit, what was y'all's first step? Did you just start factoring it straight up, or did you try to plug it in first? You factored it right away. Yeah. Um, Really, if a function, and we've kind of seen this, the three-step definition of continuity says that if the limit from the left equals the function value, which equals the limit from the right, then the function's continuous at that point. But it is an if and only if theorem. So if you turn that on its head, you could say, hey, if the limit from the left equals the limit from the right, which means if the general limit exists and it equals the function value, then the function's, or if a function is continuous, sorry, then the limit value is the function value. So really, what's going to kind of be our default first method when we have to evaluate a limit, believe it or not, is direct substitution, okay? Unless it's a special function or a piecewise function, if you plug in a number and you get an output, then chances are that function is going to be continuous at that point, and that's also the limit value, okay? So if you do plug in a 3 here, I think you do get 0 over 0, okay? And you don't want to just assume that, because there might be a problem where direct substitution works, and if you start factoring, which could be sometimes challenging, where direct substitution would have worked, but we're not trained yet in that respect. So I will tell you again now, try direct substitution first. We do get 0 over 0. Now, when we get to 1.4 and then beyond, we'll return to limits later in the year, you do want to indicate that you've plugged in. So writing 0 over 0 kind of up to the top right corner is a good indication that you've done that to anybody looking at your work, okay? So now we know that because it's two polynomials, 3 is a root. What's the corresponding factor? X minus 3, right? If 3 is a 0 or a root, x minus 3 is a factor. And that's the one that's causing the 0. So we know we're going to be able to factor and divide that out. The first rule of factoring, though, in the top is to pull out a common factor. So if I pull out an x, I'll be left with x squared minus 9, which Ella, we know is a difference of squares. And so if you want to go right to x minus 3, x plus 3, that's fantastic. And then on the bottom, we're going to get x minus 3 times, I guess, x minus 5. And again, because we started as a limit, we need to make sure we're writing the limit in front each and every time until we evaluate it. So at this point, the part that was causing the 0 over 0 is gone. And now we can use whatever's left to find the y value of what's left, which will end up essentially paving over the hole that the original function started with. So factor, divide out, and plug back in. So now when we plug in, we don't need to write the limit anymore. We just get 3 times 3 plus 3 is 6. All over 3 minus 5 is negative 2. And if this were a free response, could we call it a day? Could we be done right there? Yeah. But if we continue, what do we get here? We get negative 9, right? Yes. Yeah. If you have the right answer here, and then, you continue on and you put like 9 instead of negative 9, yeah, then you've lost points. So, yeah, you really want to, on a short answer, you really want to stop when you have a numeric answer, because there's no bonus points for going past that. You waste time, because tests are time. So that's kind of a sacred commodity that you're losing. And then you can only lose points. So, yeah, just be careful. All right, so negative 9. Now, for what it's worth, what if I ask you this? kind of an add-on. We will have a quiz tomorrow, so maybe these make good quiz questions. What would be the limit as x goes to 5 of this function? By the way, I can't just put f of x here because I never named it f of x. So unfortunately, I'd have to rewrite the whole thing. But what would the general limit be as x approaches 5? Well, yeah, if you plug in to the very beginning, you're going to get a 0 in the denominator again. And depending on which version you plug into, the original or the one without the x minus 3, you're going to get a non-zero in the top. Right. And so that tells us that there's a what at 5? A vertical asymptote. And if I ask you for any limit on a short answer for your response at a vertical asymptote, whether it's from the left side or the right side or the general limit, guess what you can always put as an answer? You could always put does not exist, because if the limit goes to infinity or negative infinity, infinity is not a limit. By definition, it is infinite. So you can put DNE. You can put DNE. All right. And you could spot that right here, you know, because you know that there's a vertical asymptote. Now, later on, we're going to study them in a little bit more detail. If it's a multiple choice question, it's going to ask you for the limit from the left or from the right of a vertical asymptote. Thank you. Then you're going to have to commit to either positive infinity or negative infinity, because DNE won't be an answer choice, but, you know, that'll be a pretty easy thing to figure out. So, yes. Did you have a question now?
Yes, I was going to ask you, on like a first question, are we allowed to write VA or do we have to write vertical asymptote?
Oh, good question. On the actual AP exam, which is May 9th, today is National Dog Day, but it turns out that May 9th, 2022 is also National Non-Abbreviation Day. And so you would celebrate by not abbreviating anything. Anything that you turn into me prior to that date, feel free to abbreviate. Vertical asymptote is VA. Rolling on the floor laughing is RLLF, whatever. I guess. Okay. So anyway, but on the actual AP exam, you don't want to abbreviate. You would have to write out vertical asymptote. Very few things, like maximum, they'll accept max. Minimum, they'll accept min. The intermediate value theorem, they'll accept IVT. There's a few things, okay? But, oh, I will. Absolutely, I will. Okay. DNE, by the way, is acceptable on the AP exam. Okay. DNE is good. All right. Any other questions? Awesome. Okay. So, as we already now know, well aware of that, prior to, I guess, pre-cal, the limit value and the function value were pretty much exactly the same, because the functions that you studied early on were polynomials, and they're continuous everywhere. So when a function is continuous everywhere, the limit and the function value are the same. There's not really a need to have the idea of the limit. And then when you started getting into like holes and vertical asymptotes, there were ways to talk about it without defining the limit. But now we know that the limit is a really, really important tool in addition to function values, because it not only allows us to describe behavior to the left and right, but when we do have a discontinuity, it gives us a way to describe that, you know, formally. And we know that they can exist independently of each other, right? And it's only when all three exist, left-sided limit, function value limit from the right, and equal each other, now that we have that special property of continuity at a point. Okay. Let's look at example 7. This is, of course, a piecewise function. You can spot it because it has the open brace, and it's kind of like a monster, right? but not like an ogre monster, more like an Elmo monster, kind of like a friendly monster. Nothing to fear really, but it's defined to be several different functions, in this case two, and it's defined on non-overlapping intervals. That's important, right? So in this case, it's the parabola x squared when x is less than 2, and our old friend Mr. Line when x is greater than 2. It says to algebraically determine the following. Thing we always want to get in the habit of doing is finding the domain. All right, now for the domain of a piecewise function, you really got to look at two things. First of all, you want to look at, and the order is not really important, but I typically look at the pieces first. X squared by itself is a polynomial, continuous everywhere, right? Domain is all real numbers. 2x minus 1, a line by itself, the domain is all real numbers. What are we trying to avoid when we look at individual functions that restrict domain? Division by 0, of course. That's just a handful of numbers. If we have an even root, like square root, fourth root or something, then we have to have positive numbers or 0 underneath it. And then, of course, if we ever have a log, which will come up later, the argument has to be positive. So if it clears those hurdles, the domain is going to be all real numbers. Unless, of course, it's trig, like tangent of pi halves and stuff. But anyway, x squared and 2x minus 1, domain of all real numbers. Now we look at the interval where it's defined. The parabola is defined only to the left of 2, and the line is only to the right of 2. So what x values work? What x values will generate an output? Everything except the 2. Yeah. And that one is by explicit lack of definition, right? So you got to be real careful when you read there. There is no equal sign on any one of those. So we know 100% now this function has no possible way of being continuous at 2, because 2 is not even in the domain. There is no bridge there. So when we write the domain, we want to make sure that we write it in the correct fashion. So big D subscript F. Big D is for domain, not Dallas. Subscript typically is what we do as a courtesy to the function. We put its name there, and then we put colon, not equal, okay? And there's two ways to do it. You can use set notation, the set of all x, such that x is not equal to 2. Set builder, that's what this is. The vertical bar, remember, means such that. And this one has the most flexibility because, you know, you could pretty much just say everything except 2. Now, if we don't define which number set we're talking about, the default number set is the real numbers, okay? That's important. So you don't have to say where x is an element of the real numbers. It's only if we're looking at a subset of that, like integers, that we have to define that. Of course, if you want interval notation, you could say, I'll put or, d subscript f would be from left to right, negative infinity to 2 parentheses, 2 to infinity. That's how you step over 2. Interval notation has to be from left to right. Infinity and negative infinity always get parentheses. Okay, cool. Letter B. What would be the limit from the left of 2? Well, yeah, we could either graph it and look at the graph, but for a piecewise function, it's very easy. You just look from the left of 2 is less than 2, right? Left of 2 is less than 2. They both start with the less sound. So you can actually use direct substitution, right? And so you could just say 2 squared or 4. And again, you could put it below it, or you could put it to the side because it's just a single calculation. All right, whichever one you prefer. Now, the reason that works is because if you were to sketch this function, here's how you sketch a piecewise function, in case you're wondering why we could just do that. 2 is kind of the important point. That's where the relay baton is passed, hopefully successfully. And you know it's going to be the parabola coming in from the left. So you want to know at what y value does x squared stop at 2? So you plug it in, you get 4, and then you would put an open circle there, right? Because it's strictly less than 2. But it gives you a target. And now you could draw the parabola coming down like this. Well, that's exactly why if we want the limit from the left of 2, you don't need to worry about the graph. You just plug in wherever you see the less than. We don't even care if it's a solid dot there, do we? Because the limit doesn't care about the function value. Good. What would be the limit from the right of 2? Very good. 3. Again, right of 2 is greater than 2, so by direct substitution, you get 4 minus 1, you get 3. I'll do this one like that. And again, the reason it works is very similar. If you were to sketch the piecewise function, you would be looking to see, okay, at what y value does this graph start? And because it's strictly greater than 2, you would come over here to 2, 3, put an open circle, and then because it has a slope of 2, you just draw kind of a line going up like that. So that's kind of what the graph looks like. But we don't need to know what the graph looks like to evaluate the limit. All right, part D. What is the general limit at 2? Does not exist. Good. And that goes back to the limit theorem. The limit in general only exists if the two one-sided limits are the same finite number. Otherwise, it's D and E. No, not if it's just asking you. If you needed to put a since statement, it would say justify. Yeah, the just. Yeah, and then that's a good question. Let's just say evaluate this and then justify. In case it was asking, you would say since or because is really the better word. Because, and here's the thing: if you've already computed these and they're equal to numbers. Very good. You could just say because 4 does not equal 3. It's a little bit faster than writing the limit notation all over again. Okay. And when we're saying, hey, well, what 4 and 3 are you talking about? We know you're talking about that 4 and that 3. Because without parts B and C already in place, this seems very, very arbitrary, right? You might think that it's okay to say D and E because 7 doesn't equal 43, no, 44, right? Very arbitrary, but it's not arbitrary at all. 4 and 3 are up there, okay? Good question. All right, now f of 2 is also does not exist, all right? We knew that from the beginning. Now, if you're looking to evaluate f of 2 and it was defined there, that's where you're looking for the equal sign, okay? So the limit from the left is the less than. The limit from the right is the greater than piece. And this is when you're evaluating it at the relay point, okay? And the function value would be look for the equal sign. All right? If I were asking you to find these same quantities, but at x equals 0, well, now it all takes place right there on the first piece, doesn't it? Yeah, because it's only really important in this case because it's at the point of exchange. And then discuss the continuity at 2 based on the 3-step definition and justify. Okay, so of course we know that it's not. We've already sketched the graph, but you should be able to tell from the evidence. So we'll say F, always complete sentence. Don't ever use it. Okay, don't ever use the word it. F is not continuous, and then you state where at x equals 2. That usually gets a check, comma, because, and then I'm going to put an open brace here because there's lots of different ways we can do this. What would be one way? Right? Because, I'll just put that, because f of 2 equals d and e. If we've already collected the evidence, you could say because 4 does not equal 3, right? That means the two one-sided limits don't equal each other. You could say since the general limit as x goes to 2 of f equals DNE. You could do that as well. Yeah. No, you don't want to, not necessarily the domain, because that's not really per se part of the three-step definition, but it's really closely related to this, right? Because 2 is not in the domain, the function value there doesn't exist. So that would be the reason you would cite. Okay. Yeah. Correct. Yeah. And again, it's because we're analyzing it at the x value where it exchanges from one graph to the other. The left-sided limit is essentially what the function value of the left-sided function would be at 2. And again, we don't really care about the function value because it doesn't really matter if it's solid or open. That's going to give us the limit value from the left, right? So the limit from the left of 2 would be, if you follow the graph, it would be, okay, it would be the value of the open circle at 2, which we know would be at 4. And what would be the limit from the right of 2? Follow the graph coming in from the right. It's coming into the open circle at 2 comma what? Well, it would be what the y value of the line would have been, okay? So again, for the limit, we can use direct substitution as long as it's on either side because it tells us what the function value either is or would have been, but the limit doesn't care. Now for the function value, it has to be DNE because it's not defined. But if I had thrown, let's see, if I had thrown an equal sign into this top one, let's say the top one was less than or equal to instead of just less than, it would certainly change the domain, right? The domain would now all be all real numbers, but it wouldn't change the limit from the left, even though this would be filled in. It wouldn't change the limit from the left. It wouldn't change the limit from the right. It would change the function value though, right? The function value would now be 4. It would be the same as the limit from the left. And similarly, if I had, you know, an equal sign down here, it would change the domain. It would be all real numbers. But again, it wouldn't change the limit from the left. It wouldn't change the limit from the right. But now the function value would be 3, right? It would be the same as the right-sided limit. So they do exist independently. So that's what makes piecewise functions a little bit different. Okay? And again, if I were asking you for the limit as x approached 0, like right here, then we wouldn't even care that there's a line over there to the right of 2. Now we're just on the left-sided piece. Now we know at 0, it's just x squared. So the limit from the left is 0, the limit from the right is 0, the function value is 0, it's continuous there. Yeah. It's only because it's at that point of exchange. So let's go ahead and look at part G. What is the type of discontinuity now at x equals 2? It's a jump, right? And again, we can see that from the graph, but it's easy to spot from the evidence as well. It has nothing to do with the function value in this case. It's because the left side limit's 4 and the right sided limit is 3. As long as they're both finite, they have to be going to a finite value. If they're different, they're landing at different y values, you have to jump from one y value to the next to keep going. All right. So we'll say that f has a jump discontinuity at x equals 2. And you think it's removable or non-removable? It's non-removable. Here's what makes it non-removable. You can't put a function value down anywhere at 2, whether it's already there or not, and make it continuous. You can't fix it with a dot like you can with a hole, right? Okay, so that's what makes it non-removable. So that gets us into the definition. Oh, it says the graph of f of x. Yeah, we kind of did that already. Yeah. So here's the definition now in terms of a limit. If for some function f of x at a finite value of x, if the limit from the left is L sub 1, a finite y value, and the limit from the right is L sub 2, another finite y value, where L sub 1 does not equal L sub 2. And notice this part, regardless of f of c. F of c could be not even defined, like in ours, or it could be defined to be either one of the endpoints. Who cares? Or it could be defined to be somewhere above or below. Doesn't matter. That'll affect the domain. That'll affect the function value. But because it's a non-removable discontinuity, it doesn't affect the discontinuity itself. Then the function has a non-removable jump. And in this case, we just say at x equals c. We don't list it as an ordered pair like we do the whole, right? In fact, you can list the whole also as just at x equals, but it's preferred to have the ordered pair because it's a point discontinuity. This one, we just refer to it at the vertical location, okay? And then here's a real life photograph of a jump discontinuity in the real world. Yeah. This is not Photoshop. This is for real, you know, and thank goodness those cones are there. Yeah. Okay, now, since y'all are asking, I like to improve the notes a little bit every year. What if I do the same thing? Let's add one here. We'll call this example 7b. I will add this for next year. What if we let g of x now be, let's let it be x squared when x is not 2. Otherwise, we'll let it be 5 when x is 2. Okay, let's do the same thing. You go ahead and answer this one on your own, and we'll go over it after you do. The domain, what's the limit as x goes to 2 from the left? The limit as x goes to 2 from the right. The general limit. The function value. And then the discontinuity type. And then maybe a graph. Okay, so do that one. I'll give you a minute or two. I'll pause the recording here. Okay, so this one was inspired kind of by Lauren's question, which I like. We've got g of x now is still a piecewise function, still easy to spot. You got that open brace, but now instead of defining it to be two different functions or two different equations on either side of 2, this one says, hey, let it be x squared everywhere except at 2. That means on the left-hand side and the right-hand side of 2, it's x squared. And then when x is 2, let's explicitly define it to be 5. Let's do the graph first because I think it'll help inform everything else. But once we see that, then in the future, we can get the analytical stuff without the graph, which is really what we're looking for. So just imagine that it were just x squared, okay? If it were just x squared, it would come in here, bounce, y-axis symmetry. It would look like that. The only difference is it says, hey, when it's 2, 1, 2, don't use x squared. Okay, I won't. So I'm going to come up here and just wherever it intersects, I'm going to do that. Okay? But then it says, When x is 2, let it be 5. Now, here's the deal. I need to know where to put the point 2, 5 in relation to the graph. Does it fill the hole back up that I just erased, or is it above or below? Well, yeah, we can use direct substitution. 2 squared is 4. So that's going to be the singular point that we got rid of. And then right there at 2, I'm just putting a solid dot. There's what the graph looks like. Okay. Now, let's look at the domain. The domain should be all real numbers. You look at the function itself, x squared, it's defined everywhere, except now explicitly at 2. But hey, we redefined it to be something else at 2. So it should be all real numbers. And for all real numbers, you could just put the double bar R. Or if you want, you could put, if you're really in the interval notation, it's kind of fun to draw the infinity symbols maybe. I don't know. Okay. The limit from the left of 2. Well, you can see clearly from our graph now that it's going to be 4, right? Which is the same as the limit from the right. So how would you know that without the graph? Well, remember what we just did in the previous one. If we were looking for the left-sided limit, we were able to plug it into the function that defines the graph to the left of 2. Well, which function defines it to the left of 2 and to the right of 2? X squared. So when it's a not equal sign, you can find the general limit first, actually, by direct substitution, because it's both the left and the right. So you would get 4, 4, and 4, okay? When it's a not equals, same function on either side. So, and the function would otherwise be continuous there, right? G of 2, well, that's 5. Type of discontinuity, it's going back to the first type, right? We're going to say there's a hole, and we're going to say it's at, is the hole at 2, 4 or 2, 5? 2, 4, right. So 2, 4. You could also say at x equals 2, but of course that doesn't give as much information. Now, if we had to justify, let's just do this. G is not continuous at x equals 2. It would be because, and if we've collected all of our data, very good. If we have our data collected and it's labeled clearly elsewhere, we could just say 4 doesn't equal 5. If you haven't labeled 4 up above with the correct limit notation, the general limit or the one-sided limit, either one, and you haven't labeled 5 clearly as G of 2, you can't just say 4 equals 5 there. What do I mean by that? I mean that when people are taking a free response or a quiz and they're collecting their data, you know, instead of doing the limit from the left, the limit from the right, and the function value, they'll say 2 squared is 4, and then they'll do 2 squared, they'll do 5, and then they'll do 2 squared is 4, and then they'll say 4 doesn't equal 5. Well, I can kind of tell with 23 years of experience what you're doing here, here, and here, right? And maybe y'all can too. That looks like you're finding the left-sided limit, the function value, the right-sided limit. And sure, 4 doesn't equal 5. But would you get credit for this? No, because like, what is this garbage, right? It's not labeled. It's a bold answer. Now, if this were a multiple choice question for whatever, however they phrased it, show as little or as much work as you want. Yeah. Right. Grow some hair, buddy. Bald. Okay. Okay. Everyone good on that? All right. So left side, right side versus not equal. Okay. Yes. Yeah, there's only one type of removable discontinuity that we study, and it's the hole. So here's what the difference is, right? If you can take a manhole cover or a bridge and put it somewhere down at that discontinuity vertical location and make it continuous, it's removable. So like a hole is removable because all I got to do is plug the hole and it's continuous, right? But if you look at the jump that we had up here, notice there is no manhole cover, but you're allowed to take one if you want. Can I put that manhole cover down anywhere to make it continuous? No, I can't. So that's non-removable. Yeah. Now, later on, when we have vertical asymptotes, you may have a graph go up on this side and a graph go up on this side. They go up forever and ever and ever and ever, don't they? And as they go up forever, they get closer and closer and closer together. Someone who's a smarty britches might say, well, eventually they're going to get so close that you can just like put down a point and make them connect. And I'm like, get out of here, bro. Get out of here. Go back to your losers club. Ooh, that's a little harsh. That's a little harsh. No, in reality, sure, you're going to be able to bridge that gap, but they're going to keep going up beyond there, right? Maybe with electricity, you know, you don't want to do that. But in theory, no, still non-removable. Okay, we can't start example 8 without finishing it. So yeah, we'll just stop there. Y'all can go to lunch, and we'll pick up there when we get back.